Okay, alright. So, what we have here is the exam from fall of 2021. So this is the exam, test 1, that everyone took last semester. It is very similar to the one you will take this semester, not the same questions, but generally the same format. This is important. Take note of this, take note of this. You guys get 4 pages front and back of handwritten notes. Use this to your advantage. If we are working with binary, you will see a little 2 underneath the number. Do not think this is like 10 trillion. If we are working with hex, you'll see an OX. The rest is just general advice. So, first question right off the bat. What is Moore's Law about? How we use Moore's Law to predict computer performance. So this is something you guys went over on like the first day of class, literally like the first thing he mentioned. Can anyone tell me what Moore's Law is?
Was it something that it doubles every year?
Every 2 years. Every 2
Okay.
years, specifically what doubles is the density of transistors. We can get twice as many transistors on a chip every 2 years. So according to Moore's law, if the CPU frequency was 500 megahertz in 1998, what is the CPU frequency in 2004? So if we remember, it doubles every 2 years. So from 1998, I'm gonna just type this because my handwriting is awful. Whoops. All right. From 1998 to 2000, it doubles once, right? That's 2 years. And then from 2000 to 2002, it doubles again. Then from 2002 to 2004, it doubles again. So it doubles 1, 2, 3 times. So that is 500 megahertz times 8, which should give you 4 gigahertz. That's a dollar sign. 4 gigahertz as your new CPU frequency in 2004. Let me make sure I'm not making a fool of myself. Yep. Does that make sense to everyone? Any questions about that?
So, how is it 8? How did you multiply by 8?
So, every 2 years, the frequency doubles, right? So we are saying we have a computer or we have a model in 1998 that has 500 megahertz. What is this going to have in 2004? So we have 6 years in between. Sorry about that. 6 years in between 1998 and 2004. So it doubles from 1998 to 2000, doubles again from 2000 to 2002, then doubles again in 2004. So if it doubles 3 times, that's 2 to the power of 3 or 8. So we multiply our final answer by 2 to the power of 3 or 8, and we get 500 megahertz times 8 is 4 gigahertz.
If you want to list it out a little bit more detailed, you can do 500 times 2 and then that answer times 2 again. You can just do the individual parts if you want to. To say if it like the first time would be 500 times 2, which would give you 1 gigahertz, and then 1 times 2 would give you 2 gigahertz, and then times 2 again would give you 4, and then times 2 would give you. All right, yeah, that's 4. So and that would be 3 different times.
Yep. Any other confusion on that?
No, thank you.
Anyone else? All right, moving along.
Actually, would
Um,
we
Pardon?
Sorry. Would we be counted wrong if we kept it in megahertz instead of converting it to like gigahertz?
Nope. Nope. If you put 4,000 megahertz, it's still correct. I mean, technically you're supposed to use gigahertz, but we're not going to mark you wrong for that.
Yeah, it's the same thing, just different notation.
All right, Joe, you take this one.
All right. This one really is kind of just more of a fact, not really computation. But what this question asks is, it's talking about based on program execution on hardware. List 2 steps that are needed when we want to execute a program written in high-level language on the computer's hardware. I believe there's 4 steps, but in this question, you can as long as you just have 2 here, you'll be good to go. So the first step to go from high-level language to execution on the hardware is the first step is going to be compilers are going to take in the high-level language and they're going to compile it down to machine-level instructions, which is assembly code. And then after that, what's going to happen is assemblers are going to take the instructions that are in assembly and they're going to translate it into binary. So you're going to go from like assembly instructions to the actual binary via the assemblers, and then yeah, and those are 2 steps. There are 2 other steps that you could list as well to say after this. What would happen is the computer's operating system, it would take this binary format that's been translated with the assemblers, and it's going to actually execute. It's going to pretty much bridge the gap and take this binary and actually execute it on the hardware. And then once you get that, the hardware is actually going to execute it instruction by instruction in that binary format.
All right. Any questions, y'all?
As long as you get 2 steps, though, you'll be good. I recommend going from the highest level to lower level because it just kind of makes more sense. So really just the compiling and then the assembling would be 2 very good steps to kind of do there.
All right.
I have a question.
What up?
For the 4 sheets or 4 back and front, can we write whatever we want on it?
Yeah,
So technically, we could write all the answers to these questions on it.
Yeah.
Wow.
that's what I
All
did.
right. Okay, thank you.
All right. Number 3, give an example of using the idea of abstraction in hardware and software. An API. So when you are like, I haven't used Java in God knows how long, but you usually are calling like system.print or whatever, right? You are not making manual operating system calls to the terminal output port. So there is some kind of abstraction that Java is kind of handling all of that nasty stuff for you. So an API is an example of abstraction. Totally blank there for a second. All right.
And that abstraction, that question, there's a lot of different things you can put. I think when I took this test, I actually put an operating system, because an operating system essentially is going to take in whatever you want to do and actually execute the hardware. It's kind of like it bridges the gap between you working on a software program and the OS handling all of the really low level stuff on the hardware. So an operating system would also be another idea of abstraction there.
Yeah, for this question, I'm pretty sure that these first 3 questions will in some form absolutely be on the test. They have been pretty much every year. As long as you can justify your answer, there is no one correct answer. So if you can come to us and say, here is an example of an abstraction, here is why, 9 times out of 10 you'll get the point, even if it's something absolutely crazy. All right. Pardon?
Can I ask a quick question about question number 2?
Your question number 2, go ahead.
So whatever. Okay, so it says like there are many other steps. So in which lecture can we find like all of them? Is this a past lecture?
I think it was one of those earlier on lectures where it was talking about the process of going from high level to low level, and
Okay.
in there it talked about compiling and assembling, and then the operating side of things, where the operating system is going to take the binary format and actually put it and actually execute it on the hardware.
Yeah, I think there was a lecture that talked specifically about C compiling.
Mm-hmm.
That is a good resource.
Okay. Thank you.
All right, hand this off. AB to Joe. What are the 3 major components of a computer?
I mean, one component is the CPU, which is essentially the brain of the computer. It's going to run all of the instructions that it's been given and actually do the computations to give some sort of output. So the processor is, one component. The next component is like memory. Your memory is going to be where things get stored temporarily for the CPU to actually use and actually, perform operations on. So it's just like temporary storage for operations to sort of take place. The final, I mean, there's a couple of different things, but the third, I guess, could be input-output programs where, like, you have your keyboard, monitor, and all of your accessories to actually interface with the program to actually, do something. So that's another big component. I mean, there's a bunch of different components that you could say right there, but the CPU, memory, and I/O are probably the bare bone major components.
All right. So here we go. Our first computation question. Well, okay, second computation question.
I think you skipped number 5.
Pardon?
I think you skipped number 5.
This is number 5. Number 5 is a multi-part question.
I think you wrote the
Oh.
first thing above to get it on the same page. But
Yeah. This is part of number 4. Sorry.
Oh, okay. So
No,
what is number 5?
Yeah.
Number 5 is the one we're on, yeah.
Okay.
Oh, okay.
So this looks scary. This looks awful. But the first thing I want you to notice, remember the trick that every 4 bits is a hexadecimal digit. So let's work backwards. Hex digit. 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 And then we need to add a 0 here. Hex digit. Okay. So immediately this problem becomes a lot easier because we're no longer trying to like convert 30 trillion or whatever this is. We just need to convert each one individually and then at the end concatenate them. So who wants to give it a shot? Who thinks they can do this?
Like as in like do that like whole thing.
Yeah.
I mean I can probably go ahead and try real quick. So for me, like I kind of focus on like each 4, and I start at like at the right.
Okay.
And I know that like and on the right that's going to be like that 5 right there, since it's going to be 5 I think. And then
Okay.
and then that one is going to be a 1, since like that one's going to be a 1.
Mm-hmm.
And then for this one, that's going to end up being a letter, because it ends up like it has like 8, 4, 2, and when you add that up, that becomes 14, or I think that'd be E.
Yeah.
And then for that one, that'd be 15. So then that turn into an F
All
because
right.
that corresponds with 15. And then from there you have 0, 1, 1, 1. I think that'd be like 1. End up being 6. I'm thinking.
That wouldn't be 6.
Ooh.
Think about
Let me doubt.
there
Oh, that'd be
is.
7.
Yeah. There you go.
Okay.
Remember, if you have a string of 1s, it's obviously going to be odd, an odd number. And if you remember your powers of 2, like this is 2 to the power of 0, this is 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. If you have a bunch of 1s, it is 2 to the power of 3 right here, which is the first 0 minus 1. So if we have like in binary 1, 1, 1, 1, this is the same as 1, 0, 0, 0, 0, 0. Now 1, 0, 0, 0 minus 1. And this is 16 minus 1. So this is 15. Does that make sense? Does that trick make sense?
Kind of.
Hmm?
Yeah, I think it kind of starting to make sense there.
Okay.
Um,
Alright, so keep going.
and then for that one, that's going to be. I think that should be 10, which would correspond with A.
Alright.
And then for that one, that would just be a 3. That next one to the left. And then since we're adding as that'd be 0, 1, 1, 1, right?
Mm-hmm.
So then that just end up being a 7.
Alright. Now let me 73A7FE15. Yep, so this is the answer. OX 73A7FE15. And did you see how we did not need to like convert 30 billion from binary to hexadecimal because we did this chopping trick of doing 4 bits at a time? Remember that, because he will probably also give you an absolutely horrifying looking binary number that will be absolutely impossible to convert unless you do this 4 chunk trick. Alright, Joe, you take number 2, or 2 of part 5, or part 2 of 5.
Yeah, I gotcha. So this question, it wants you to take the number. It wants you to take the decimal number of -43 and put it into an 8-bit binary representation using 2's complement. So there's really 3 sort of steps to 2's complement. The first step is you're going to convert the actual number into binary. You're just going to take the number. You don't worry about the sign at this point. So you just kind of want to convert 43 into binary. So a good way to do it is you can do just kind of break it up into the powers of 2. So you just take the largest power of 2 that can actually make up this number, which would be 32. And then you just kind of add up all the numbers. So it'd be 32 plus 8 plus 2 plus 1. And yeah, that should give you 43. And then what you're going to do is you're going to write this in terms of binary, which would be the 0 spot, the 1 spot, the 3 spot, and the 5 spot. The way I like to do it is I like to write the placement of the number above and then kind of just fill in where I'm at. But you kind of just have that, and then you put your notation of 2. And then what you're going to do is you're going to take this binary representation and you're going to do 2's complement on it. So first thing you're going to do is you're going to invert the number to say you're going to just pretty much flip the bit where wherever it's 1, it's 0, and wherever it's 0, it'll become 1. So it'll be 0, 1, 0, 1, 0, 0.
We made a mistake.
Did I? I think I probably. Yeah, you got it. Oh yeah, and make sure you fill it to it. It'll actually be 8. You have to have 8 bits. So just fill wherever you need a spot, just fill the front with zeros because it'll be just a regular positive binary number, and then you'll flip those to 1. After flipping it, what you're going to do is you're just going to add 1 to the very far right, and in this case it's 0, so it just becomes the same thing with a 1 at the end. And yeah, that should be it. And then I like to check by splitting them up in 4s, so 1 1 0 1 and then 0 1 0 1. Yep, that's it. Any questions about that?
So, quick question. So, so you had the first bit from the right 0, and you had like multiple other zeros. Let's say if the first bit was not available, and from the middle ones was 0, and the rest of them was 1. How what is the best way to do that? Basically, just add them up.
Are you saying like to calculate 43 to get the binary representation of it?
No. So the last bit was 0, right? So if those bits were like 1, okay, and the 0 was somewhere in the middle, like let's say if it was a different number, so we just add them and like just put their
Oh, you're saying if the last thing is 1, and then if you need to add 1 to
yes.
the last one. Yeah, so in binary, what you'd do if the last thing was 1, it would be 1 plus 1, which is going to be it's going to be 0, and then you're going to carry over the 1. So it's going to be 1 plus 1, which is 0, and then it'll carry over to the next line, and then you kind of just use that carryover 1 to determine whether if it's a 1 or a 0 in that case. To say if the carryover is like 1 plus 1 plus 0, then it's still just carry over again, where you'd have a 0 and then a carryover. And if it's like if it's 1 plus 1 plus 1, it would have a 1 and then a carryover of 1. It kind of just depends on what your next digit is. So.
Okay, thank you.
Mm-hmm.
All right. So, piggybacking off of that, what is the 4-digit hexadecimal representation of the decimal number -43? So, we have to remember from the first problem that we have this way of chunking the number into 4 bits for each digit, but it wants 4 digits and we have 8 bits, which only gives us 2 digits. But remember, we're in 2's complements, we're dealing with a negative number. So, we have this, and then we have, this, right? And if I'm not mistaken, this is five, and this is, I can never remember.
D.
B. Thank you. Yes, thank you. So we have B5.
Sorry, not B, delta.
Delta?
Yeah, because it will be 8, 4.
It's
Oh,
13.
D.
13.
D.
Yeah.
Okay. Okay. Yes, I am not the best at memorizing this. But we have 2 more digits. We only have 2 hexadecimal digits here. It asks for 4. But remember, we are in 2's complement. So everything to the right, left, must be 1s because those are our sign bits and we inverted the number. So we then have FF because everything to the left is 1s. So the 4-digit hexadecimal representation of the decimal number -43 in 2's complement is 0x, let me do this like down here, 0xFFD5. Any questions?
Could you explain the FF part one more time? Sorry.
So we are in 2's complement, remember? So that means everything to the left is ones, not zeros, up until a certain point, because we want to indicate with a sign bit that our number is negative. So if we have a 4-digit hexadecimal number, we have a 16-digit binary number. Essentially what we are doing is converting our number from that to 1, 2, 3, 4, 5, 6, 7, 8, right? Because that is how we get 4 hexadecimal digits. And then again, we can do the same chunking, blah, 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 blah. That makes sense to everyone?
And if it was positive, then we would just have 0xdf.
If it was positive, yes, we would fill with zeros, and then we would have, yes, 0, 0, df. But that would be if the binary number was positive. If 43 was positive, we'd have a totally different hexadecimal thing. Just catching myself there.
I'm
All
pretty
right.
sure zeros and hex are also just cut off for
Yes, so
adding.
it would be just 0xd5. I think the person, they said just 0xd5, and that is correct.
Yeah.
Okay. Joe?
Okay, yeah, so here we have a half word, which is really, don't worry about the terminology. This is just another binary representation at the moment. And right now it says that this binary representation, it's already in 2's complement. And what we want to do is we want to find the pretty much the decimal base, a number that it represents. So it's kind of just doing it backwards instead of like negative 43 to the 2's complement. Now it's just going backwards. So a good way to sort of start this one off is divide everything by 4s, like section everything up into 4s, and then sort of see what you get from that. Another big indicator here is since it's in 2's complement, this is going to be a negative number. All of those ones in front, in the section of 4s, all of those ones kind of just represent a negative sign. They're not really a part of the number. They just kind of represent the sign. So,
Well, wait, hold on. Let me interject for a second. It being in 2's complement does not necessarily mean it's negative, but this top bit being 1, that indicates it's negative.
yeah, the leading one.
Yes, but as you'll see when you convert it, all of these extra ones in the middle will go away, and you will not have to convert a very nasty number.
Right. Yeah. So yeah, the leading bit is going to be what's negative. It's really once you see that leading bit and then all of the ones, that's going to indicate the negative sign. So the main part that you need to worry about here is the first 2 sections, which would be the section where it says 1001 and 0101. Those 2 parts. We're gonna actually convert those to decimal. Just well, first what we're gonna do is we're gonna you're gonna flip those around, or I think you're gonna actually subtract. You need to do 2's complement again, where you subtract 1 from it to where you'd get 100101000, and then from that you're going to invert it to where it'd be 011011011. So after you subtract 1 and invert it, you'll get this binary number that is going to be your actual decimal number in binary conversion. So from here, you're just gonna, just convert it to, the binary number. So it's 1 plus 2 plus 8 plus 60. I think, is that 64 or 32? I've already lost track.
1, 2, 4, 16. Wait, 1, 2,
Yeah.
8, 32, 64. And if I'm not mistaken,
Yeah. 32, 64. Yeah. And then that's all of those added up together will be 107. Negative 107.
Yes. So the number ends up being negative 107.
Because you have to maintain the sign that you have. So yeah. Any questions on that?
Wait, so how did you know it was negative again?
The leading bit, when they give you this binary number, that leading bit, if it's 1, that means it's going to be a negative number. If it's a 0, then it's going to be a positive number.
How do you know it's not just the positive value of that bit?
Because we are saying, okay, so actually the word half word is kind of meaningful here. We are saying this is the largest value, the largest length binary possible of this size, which means that we can't even store positive numbers that big. When we go into choose complements, we actually half our range of storable positive numbers in order to give us half of those to be negative numbers. So if we do have a 1, we do not have, and we say we are in choose complement, we definitely have a negative number, because we can't go any bigger, because when we chose, say, hey, we have a sign bit, we give up the ability to go beyond 2 to the n minus 1. Does that make sense?
Not at all.
Not at all? Okay. So, if we have an 8-bit 2 complement number, first we have an 8-bit number. What is the maximum number we can store in an 8-bit number?
That's what, 2 to the 7? Well, 2 to the 7 plus 2 to the 6 plus 2 to the 5, right?
Yep. Which is?
Uh,
Remember the trick you can use. If you have 2 to the 7th plus 2 to the 6th plus 2, that is equal to 2 to the 8th minus 1.
2 to the 8th. Oh, right. 2 to the 8th minus 1. Yes. Okay. But it's 2 to the 7th, right? Minus 1.
No, it's 2 to the 8th. We're not in choose complement yet.
You subtract 1, not from the exponent, but just from the overall term. It would be 2 to the 8 minus 1.
But it is an 8-bit, like 8 numbers, right? And it starts off at 2 to the 0 and then goes up.
Mm-hmm.
So wouldn't it be 2 to the 0 is 1 bit, 2 to the 1 is 2 bits, 2 to the 2 is 3 bits, and then 4 is 5, 6 is, I just skipped 1. 5 is, do you see what I'm saying? Like it starts off at 0, like an array.
Mm-hmm.
So wouldn't it be 2 to the 7?
Nope. It, because even though we have 2 to the 0 as like the first thing, we still have 2 choices. We have 2 to the 1 choices. And if we have 2 bits, even though like that can store up to 3, we have 2 to the 2 choices, which is 4, because remember we're including 0.
Oh, okay. I see.
So for an 8-bit number, we have 2 to the 8 minus 1, and that minus 1 is not on the exponent, which is
2 to the 8 minus 1. We did this earlier. Yeah, I'm lost. I'm sorry.
all right. It's 255. That is the highest number that an 8-bit number not in choose complement can store. But when we go into choose complement, we say our top bit, we're getting rid of it. This top bit will only be used to indicate whether or not a number is negative or positive. Therefore, the largest number we can store is, if I'm not mistaken, 127.
For a half word?
Not for a half word, for an 8-bit. For a half word, I didn't want to bother computing that. That's 2 to the power of 32. Or to the power. Yeah. Does that make sense to everyone? Why this top bit?
Think of the leading bit more as a flag than an
Yes.
actual thing.
I didn't get that 127 part.
So, when we are in 2's complement, we take away the top bit and make it a flag to indicate whether or not the number is negative or positive. So because of that, we lose a bit. So therefore, our highest positive number we can store is now 2 to the 7th minus 1, not 2 to the 8th. Because we just lost a bit.
Oh, so this only applies if the binary number is in 2's complement already.
Yes.
So if it's not in 2's complement, we don't know if it's positive or negative.
If it's in 2's complement, if it's not in 2's complement, we call that an unsigned number, which means we're just assuming it is positive. And because
Okay,
we're
I thought-
assuming it's positive, we can then use the bit that we would normally use as a flag as another bit, just so then we get an extra bit of precision.
Okay, I understand now.
Okay, cool. Any questions for anyone else? All right. Is this one mine or yours? I can't remember.
I think it's yours.
All right. So we have a one-dimensional array in C. Actually, okay.